Ready for the weekend? Who said no? How come?
No weekend. We don't have we don't have weekends, Professor. We just do homework.
So busy.
We just do homework.
Yeah, but at least you have a little more time.
No. I know.
Well, you don't have to come here and have classes to distract you.
But I have to do laundry, clean my house.
Laundry, clean.
Food.
That's what kids are for, right? Well, well, anyway. That's true. I'll review lesson plans. I'll read the next chapters. I'll start working on the next test. But I know it's not the same. I'll admit, I've never left academia. I've always been here. It seems like, go to school, take more school, and then teach. So I remember. But the day I stopped being a student and didn't have to do homework, I have to admit that was a pretty grand day. Until the bills. Well, it was good. You get married, and then we had two sources of income. I don't know why people complain. Oh, getting married, it's financial strain. What are you talking about? This is great. We got I think some extra grants that way. Yeah, one semester we both had a grant, and then with some scholarships, we got married. So I ate better, but then we could make the meals with one. It was one meal, so it didn't cost as much. Point is, I think we actually got money back that semester. Not much, but we actually got one semester. We got money back. Anyway, well, now that I've made fun of you because you had to do homework. One advantage to homework, I have to admit, I'll admit as a student and definitely as a teacher, it does give you practice and chance to work them out, and you see what's important to me. That's why I choose those for the homework. So, let's see.
The homework is not a problem. It's a grading.
The homework's not the problem, it's grading the homework. Well, I have no comment to that. On that vein, let's see. Yes. Homework 5 will be due Sunday. It's just on Chapter 6, Momentum, so at least there's less covered. But it's because that's all we've covered. Then next week we'll start, we'll get through Chapter 7 on energy and Chapter 10 on projectiles. In Chapter 10 it also discusses orbits. I'm not going to go there. So you only have to worry about the projectile motion and two-dimensional motion in Chapter 10. So you don't. Those of you that are reading along, I expect you to. So we'll see. But anyway, now you know that for Chapter 10. It's not all of Chapter 10, just projectiles. All right. I had a comment. Let's see. I went and looked on WebAssign to curiosity. Thought you guys might be interested to see who looked at the answer keys to homework. For homework 1, which was logistics, 7 people. Homework 2, 19. Homework 3, 15. Homework 4, 13. So that's around 20 to 30%. What that means to me is only 20 or 30% of you have bothered to find out for sure what the answers were and looked at my explanations. Now, granted, if you're going through, and if you've missed it enough, or you know what you got right, but you haven't seen my answers or anything, maybe you don't need it. But I thought that was lower than I expected. So just a reminder that is a resource there for you, the answers, with my explanations. Yes?
There was a little flag where you're supposed to be able to get a practice test. When you're reviewing the homework, and it says okay to key, and then above that, there's a little, some kind of square thing that's supposed to give you another test so you can practice, but nothing happened when you click on it.
Okay, that's because there isn't one.
Oh.
WebAssign has the feature that teachers can put, for example, past tests, if they had them. So if they had them and installed them, then they would be there for you. It's like them creating other assignments, so you could go. So yeah, it's not. It doesn't just make them up willy-nilly, and I haven't done that. So it's not there. So when you click on it, that's why it doesn't work. Do you have one? Well, when it comes to you. I also thought you might find it interesting. 21 of you retook exam 1, chose to. On exam 1, the average was 72, 73%. I can't remember at the moment. Those that took the retake, the average was a 94%. Everybody did better and significantly better. So they learned and got a lot more points. So there weren't as many of you that took it, but that raised the whole class average a half a letter grade just by doing that. But that was just 21 of you. Again, it was your choice. Some of you did well in the first place. So, I mean, there was even 100%. So, but I thought you'd be interested to know that. You get to drop. I will drop at the end of the semester your lowest scored homework and your lowest scored exam. It's a relief. It also means I don't have to deal with lame excuses or even good excuses. If you want to go to that wedding, go right ahead. Because since there aren't makeup exams.
Oh, the other thing is, I remember, is the web assigned.
Uh-huh.
It took me a couple of weeks to open the key. I couldn't. The key answer. I couldn't open it.
Wouldn't let you?
I
Huh.
saw something, I was doing something wrong. Or maybe I was missing some parts.
I'll have to think about that one. You couldn't open the answer keys for a couple weeks. I go in under student view to see it how you guys are, so it gets rid of all my administrator, privileges, and I checked such things. I remember looking at keys, so it let me.
I opened it after, but for 2 weeks I couldn't. And I asked my classmates to do it for me, and he couldn't either.
Under your name or under their name?
My name.
Okay, because I know
Maybe I was doing something wrong.
I know some other students did because I can see when they looked at the key, so it was functioning. So that was a special case there. I don't know, but it works now. Well, I apologize for that. Wonderful technology. Well, speaking of technology, I thought we'd do some clicker questions on momentum. See what we learned last time, re-solidify it, go over it some more, and continue on. What's that? Still on channel 41. If I change that, I'll warn you. You guys will all be yelling at me too because it won't work it for you. And oh. Hey, I learned something. The projectors go to sleep after a long time. But if you put it on video mute, so it does a blue screen, it goes off a lot quicker. They turned off on us. That's why it's not back up there. So we got a minute to kill. Any questions about momentum while it comes back up and you log in? All right, I'll open up polling then for this question and let you get started on this one. Okay, polling should be open. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Ooh, large majority. 88% think it's B. Very good. So how'd you figure that out? Momentum is mass times velocity. It's the product of the two. So let's figure out the momentums of each. 200-pound man running at 10 miles an hour. Now 200 pounds is actually the force, I want to reiterate that. Pounds is a unit of force. So yes, you could divide that by 10 and get the mass. Well, not really, because that would have to be in newtons. You can divide it by the acceleration due to gravity and get the mass. But for this problem, you don't actually have to do that, because the mass is proportional to the force, right? I mean, 200 pounds, if he's 400 pounds, it's going to be twice as much mass. So for argument's sake, we can just multiply 200 by the velocity 10, 2,000. That represents the first person's momentum. But I want you to realize that's technically not the momentum, because that was pounds, not mass. You follow? So 2,000 is a number that gets us. What's the other one? The momentum of a 2,000-pound car moving at 1 mile an hour. So that, 2,000 times 1 is 2,000. So they have the same momentum. That's how you figure out somebody's momentum. Mass times velocity. Let's try another one. Polling should be open. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you think A, some B. The majority has it the same. Why is it the same? Mass times velocity is momentum. What's not changing? The mass. Your mass doesn't change. That's how much of you are. Your weight would on the moon compared to, but your mass is the same. So since your mass is the same, you'd have the same momentum going the same speed, whether you're anywhere in the universe. All right, go. Yeah. Oh, haystack, and a farmer in a field, they build those things. It's just a big ball of hay. It's cushiony as opposed to hitting a wall. So yeah, you're going to run into a haystack where you have a little give, or you hit a wall. In both cases, it says you come to a full stop either way eventually. Yeah, you can. The car comes in this identically. Basically, you think of it, it's cruising at some speed. You hit a haystack and it comes to a stop. Or you hit a wall and it comes to a stop. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, we're split. All right. I'm going to re-ask it then. Talk to your neighbor. I'd like to see if it changes. Explain to your neighbor why you chose what you chose, and let's see if things change. Go ahead, talk away. Polling is open again, so I want you to re-vote. What's?
I remember you say that the example with the tricycle and the big car,
Uh-huh.
and the tricycle was lighter, but still.
Yeah, truck and a tricycle. Yeah, the truck's heavier, the tricycle's lighter.
Mm-hmm.
That's true. We'll get quiet. Let's see. How's the voting? Oh. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 2 of you haven't voted. You want to? Okie doke. All right, we've switched to C. More of you think C now. Good, see? You guys can teach each other. That's another resource that most students, I think, underutilize in college. If I had to redo college again, I would hook up in study groups a lot more often. It was more efficient, or at least I felt better while I was studying instead of being stressed by myself. So I encourage you guys to talk and discuss. Now, since it wasn't everybody, what's going on here is if you're coming in at the same speed either way, and you come to a stop either way, the change in velocity is the same. Your mass doesn't change. Momentum is mass times velocity. You start with a certain momentum, it's the same either way. You end with the same momentum, 0. So you have the same change in momentum. What's another word for change in momentum? Impulse. So the impulse is the same, the change in momentum is the same. What will be different? Yeah, the time and thus the force. That'll change. Force times time is impulse or change in momentum. That's what causes the change in momentum. The haystack will exert less force on you because it'll take longer. It has more time to do it than the wall. But the change in momentum is the same for both. Do you see that now? Whoa, that's not what I meant to do. All right. Ask a similar one. Polling should be open. And hopefully this one will be easier now. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. 62B, that is correct. It's the same question, actually. We just changed the objects and it stuck to the wall. But again, it's coming in, it stops. So the change in momentum and thus the impulse is the same. Concerns? Hallelujah. All right, we'll call that good. Friendly reminder that A equals that. It also is a change in velocity. This is Newton's second law. This is in your book. We did it last lecture. So if we then set these equal, because they are, and cross multiply, there's your impulse. And it creates a change in momentum, which we can write like that. So this whole concept comes about from Newton's second law. But we use Newton's third law also, because when two things collide, the force that each feels is the same, just in opposite directions. And since they're the ones in contact with each other, the time this one's in contact with this one is the same time this one's in contact with this one. So let's collide some things. Here's two. Have we used? No, I don't think I've used the air track in this class yet, have I? This is like a linear air hockey table. There's a bunch of little holes in here. And so I got a blower behind the wall here, and I'll blow air out the holes, and it will help eliminate friction, or at least minimize friction, so we don't have to worry about that. A lot of teachers like to use this for inertia, because if you give something a push, it just keeps going. It doesn't slow down, because there's nothing to slow it down, except for the ends that push on it and change direction. Remember, velocity is a vector. But yeah, it'll do this a long time. We won't wait to see how long it takes. What? The little things on the end are springy. Little metal that's just bent. I think you can see it's slowed down a little by now, but it's still going. I don't bother anymore trying to level it. But it's actually pretty easy. I can just set it there, and whichever way it starts to move, I can raise or lower until it. So we're going to do, we don't have to worry about friction. I'm going to take two of them. They're the same mass. And I'm going to have this one be at 0, and I'm going to push this one into it. What do you think will happen? So let's see, from your perspective, we got mass 1 traveling at velocity 1 is going to come and hit mass 2 that isn't moving. And when you do these collision problems, I like drawing pictures, a before and an after. It helps me understand what's going on. So if you find yourself getting confused, draw some pictures. So this is going to come in and hit this one. What do you think will happen? Mass 1 will stop and mass 2 will move? How fast will mass 2 move? Okay, and it'll move with whatever velocity that one had initially? So that's called a transfer of momentum. But he's thinking that all of this guy's momentum will be transferred to this one. Why couldn't this one give it half the momentum? Thus, this one goes off with half the speed. No, I mean, that could happen, right? This whole game is going to be called conservation of momentum. I mentioned it last time. And that means total momentum is always conserved. That's how I remember it. Those of you that are taking notes, which is not the majority, total momentum is always conserved. What?
Total momentum is always conserved?
Yep. So let's look at the total momentum beforehand. Momentum 1 is mass 1 v1. Okay. Momentum 2 is mass 2 v2. So that's 0 because it's not moving beforehand. So this has some momentum, this has none. The total is total before is momentum of one plus momentum of the other. Fairly straightforward thus far, right? All right, let's let them hit. And let's say we don't know what's going on. This will have some momentum afterwards. P1 is still M1V1, but this is fun when you get the subscripts. I don't know, we could call this A for after. I don't know. And this will have some momentum after. Now the mass doesn't change, so that's really the same thing. And the total, again, will be total after, P1 after plus P2 after. We don't know what those are yet. But there's a neat thing. This has to equal the total before. And we're going to learn about conservation of energy as well. We haven't talked about energy yet, so I can't tell you what they are, but both have to be conserved in certain cases. Total momentum is always conserved. That's why I like starting with it, plus your book does. Now your gut is right. I'm going to go ahead and tell you. Because they're the same mass, this one does come to a complete stop. And if it stops, it no longer has momentum, which means the other one must have the momentum it started with to keep the total conserved, because the total before has to equal the total after. Let's do it. All right, that one's pretty much not moving. I come in, boink, and this one stops. If I hold it so it's not moving, it comes back, boom, and it stops. So yeah, all of its momentum is transferred to his friend because they're the same mass in this case. What if I make it half the mass and do it? What do you think will happen? So it's coming. Momentum, no momentum. See the total? It's all with that one. And then, what do you think? Speed? What about speed?
Speed will be increased double.
The speed will be increased double for which?
The smaller one or the big one.
So it'll end up going twice as fast? Okay.
If that is it keeps,
I don't know. I'm asking for ideas. So she disagrees with you, obviously, or doesn't understand your thinking. Why do you think this one will go twice as fast? Inertia? Give me more. For this one? So you think this one will be going twice as fast?
Yes.
I think so, the second one.
Okay. Well, what will happen to this one?
Stop.
So, in reality, what it chose to do is that some of its momentum was transferred to the smaller cart. But he didn't give up all of his momentum. Do you notice it was going slower? So he lost some momentum from beforehand. Where did it go? Into this. But if you added up the total before, none, something, that has to be equal to, now this has less, but this has more. The total is still the same.
Even because the size,
Because of the mass is different now. Let's do it this way. Let's have the small one run into the big one not moving. What'll happen? I couldn't hear you.
The big one will move, but the little one will also probably bounce back off.
Okay, so you think it'll make this one go back a little, but this one will bounce off of it? Like a gun recoiling? Let's try it. You're right. So notice this is not moving as fast as that was initially. Let's do it again. However fast I make this one move, note that when this guy moves, it's not as fast. Let's see. So it's coming in about that fast? He's moving, but not quite as fast.
because also the mass and it is partially transferred the momentum,
Right, again, this one transfers some of his momentum to this one,
but other one has more mass.
but it keeps some in the other direction. But the total after has to equal the total before, because total momentum is always conserved. Okay. What if I do two the same mass again, but they're both moving? I'll try to make them move at the same speed. When they come back together, they should be coming at the same speed. Well, obviously that one went a little faster, but I'll try again. What do you think will happen now? Because now the total momentum beforehand, they both have momentum, right? But in theory, they have the same momentum. So this momentum plus this momentum. You know they're going to bounce off. And will they bounce off going the same speed? Or one faster? Boink. You're right. But there's something neat here. What is the total momentum? You don't even need to know the values. What's the total momentum of the system right now? 0. Good. How about now? Yeah, you're like, I don't know. I don't know how fast they're going. But I propose to you that you don't need to know to get the answer. Let's say you have a cart coming this way and a cart coming this way. M2 going there and M1 going the same speed. What's this guy's momentum? It's that. What's this guy's momentum? So you want to add them together to get the total? There's one problem here. What's velocity? It's directional. It's a vector. Remember we always had to do signs? Since these are in opposite directions, momentum's a vector. It's directional. One of these needs to be the opposite sign. So if by normal convention we say to the right is positive, then this one's negative, because they're coming at each opposite directions. So the total momentum is, well, we'll just do this. M2v plus a negative M1v. Or minus. I just did that for emphasis. Since they're the same mass, and they're going the same speed, or I'm trying to in this case, they cancel. And the total momentum is 0. Even when they're moving. If they have the same momentum in opposite directions. So, the total momentum right now is 0. How about now? 0. 0. The total. Well, that one wasn't as good, huh? 0. 0. 0. So you can see when they switch, this one's coming in with positive momentum, this one's coming in with negative momentum. Now this one goes out with negative momentum, and this one goes out with positive momentum. So their momentum's changed. They felt an impulse. Change in momentum. It made them change direction. But the total momentum's still the same. Let's do that a different way. Oh, by the way, because now it matters. That's called an elastic collision. An elastic collision. You'll need to know that. Briefly, that's where you bounce or rebound. You know, basketball would work. There's a second type of collision I'm going to do now called an inelastic collision. And that's where they stick together. There is deformation. That's like when your cars run into each other. Two cars generally don't bounce off each other. They crumple and deform and often can get tangled around each other. Or two football players, on behalf of the Super Bowl recently. They grab a hold of each other and they stay together after the collision. That's called an inelastic collision. Why do we bother differentiating? Well, for momentum, total momentum is always conserved. So for both types of collisions, total momentum is conserved. We're going to learn that kinetic energy is not conserved in an inelastic collision. But I haven't told you what it is yet. Why don't I just go ahead and do that? It's next chapter. But raise your hand if you've never heard of kinetic energy. 1. See, most of you have at least heard of it anyway. I usually just write it as KE. And it's the energy associated with motion. So it's going to have velocity. It's proportional to velocity, they found out. It was actually interesting. Historically, you can look it up. I won't tell you the whole story. But basically there was a debate about, they called it oomph. I don't know, my term. How much oomph something had. Because they knew when it ran into something that it caused a reaction. They called it, so the ball came in with so much oomph. Well, that's not a very technical science term. Are you talking about force, momentum, energy? They didn't know. Oomph. Well, what they did is they dropped spheres into like Play-Doh. You could do that, or clay, and how far the ball caused a divot. It would make a divot in the clay. And so they knew that this ball had so much oomph, and that oomph was transferred into the clay and caused it to make a certain size divot. Well, they knew what you knew at this point. If the ball starts this high, I know how long it'll take to fall that far from those formulas we had before. I didn't ask you to do that one, but remember I had you could count how long something fell and know how high up you were. So you could time it. You could figure out how fast it's going. You could figure out how high it is. You can measure that. So this ball has some oomph. Then they measured how much oomph went into the clay. How deep did it go? There's a force acting on the clay, and it caused the clay to smush. And long story short, they realized that this oomph was more like energy, not momentum. And it was proportional to velocity squared. It mattered how fast it was going, but not momentum. Momentum is directly, linearly related to velocity, right? If something's going twice as fast, how does its momentum change? It's twice as much. But kinetic energy is different. If something's going twice as fast, how much more kinetic energy does it have? If you double the velocity, what happens to this term? You guys aren't playing. I heard one person say it. I was just waiting for some more. So just help me out. Do you just not care, you're afraid to answer, or you're not sure how to do it? Because if you're not sure how to do it, tell me. I'll work it out. I just don't know what you're thinking. If you double the velocity, so something's going twice as fast, what happens to its kinetic energy? Does it have twice as much energy? Good, thank you. I see more response. All right. I appreciate it. And that's like this. If you replace the V with twice as fast, then you have to square both of those. So you get 4 V squared. So that's the idea here. And that's how they could tell. Because the divot was 4 times deeper instead of 2 times deeper. And so they knew it was proportional to energy. Because this, again, let's try another one. What if you go 3 times as fast? What happens to the momentum? 3 times the momentum. What if you're going 3 times as fast? What happens to your kinetic energy? You have 9 times as much energy. Yeah. So this is going to be important in this semester. Remembering that. So that's kinetic energy, and it's the energy associated with motion. In or during an inelastic collision, some of this kinetic energy is transferred into something else. That's why kinetic energy is not conserved in an inelastic collision. Some of this energy of motion goes into crumpling the car, or to heat, or sound. Energy is still conserved. Total energy is still conserved. But kinetic energy is not in an inelastic collision because it gets transformed into some other form of energy, and it's no longer energy of motion of the object. So, to review, two types of collisions. Total momentum is always conserved, both cases. Kinetic energy is conserved here, but not here. So you got a big chunk of the next chapter done. Now let's do an inelastic collision. These have Velcro, so they stick. The same mass. So if I have them going at the same speed, what should happen when they get here and stick together? They stop. Because what's the total momentum now? 0. If they're going the same speed, now 0. So what's it have to be after? 0. I like that one. What if I do this? What will happen? This time they won't bounce off each other. They'll move this way, but slower. This one can't bounce off because they're going to stick. But they'll move together. Any other thoughts? Ooh, half the speed because twice the mass. Yeah. If you double the mass, yeah, the speed has to go down by a factor of 2 to keep the total the same. Very good. Let's try it. So get an idea how fast that one's moving. Did you see him slow down? Takes longer to get to the end now. Let's do it again. Maybe I'll try faster. Can you tell it slows down? What if this one's going fast and this one's going slow? What'll happen? They still stick. If this one's going faster and this one's going slower, which way will they end up going afterwards? Yeah, that way. A little slower than this one, right? But this one turns around. And how you do that again, it's just, positive momentum, negative momentum. You add them together, see what the total was initially. That has to be the total afterwards. They're just moving at the same velocity now with twice the mass. Let's see what happens. Slowly. Quickly. Oh, lame. Too fast for the Velcro. Okay. Fine. Yep, turns that one around and slows this one down a little bit. Could you tell? And if we did it with a small one, what will happen? So I'm trying to do them the same speed, but this one has half the mass, so they're coming in with different momentums now, right? It's technically not momentums, it's momenta, but I don't want to confuse you. What will happen after they collide then? You think it'll go that way? Because this one will have more momentum than this one if they're going the same speed, because he's got more mass. He should have twice as much momentum as this one initially, just in opposite directions. I'm going to try to, yeah. So yeah, you got m1 traveling at v, and you'll have m2, which is half of it. So you could think of it as m1 divided by 2, going at the same speed. So let's see, the total beforehand is positive minus, does that make sense before I move on? Okay. M2 is half M1. So it's like a half M1V1, M1V1. So the total is a negative half. You see that? Because there's a 1 here. Negative 1. Half minus a negative 1. Negative half. That's the total momentum beforehand. So that has to be the total momentum after. Close. That one slowed down, didn't it? Fine. And they do end up going that way a little slower. I think I got one more for you. It doesn't have to be just when they hit. When you shoot a gun, you exert a force on the bullet exerts the same force back on the gun. It's like a reverse collision. They're going to fly apart. There's a force on each other, on them, the gun and the bullet. Same force for the same amount of time, so they both receive the same impulse. They should both receive the same change in momentum. So there's a spring here, and I've tied it together with a string. So when I burn the string, the force should throw them apart. How will they throw them apart? If they're the same mass equally, that's correct. They are the same mass. But what's the total momentum before the collision? 0. Yeah, they're not moving. That's the easy one. But they're going to be moving afterwards, but in opposite directions. So same mass at the same speed, but opposite. So it'll be mv that way, mv that way. Positive and negative. The total will still be 0. See if this works today. Yep. And boom, right back in the middle. Collisions can be fun. All right, I got to do this fast anyway. Got a couple minutes. Here's 2 balls. They're the same size, same volume. One bounces, one doesn't. If I roll them down this, they'll knock the block. They'll hit the block. What do you think will happen? Here's the sad ball. I call this one the sad ball. And this is the happy ball. Sad ball will knock it over? Maybe it was a fluke. Okay, that's a sad ball. How about the happy ball? Worse? More? Or split? It'll knock it over? So, what I'll leave you with is the happy ball bounces off. It rebounds off. The sad ball does not. The happy ball exerts enough force to knock it over. The sad ball does not. You're going to tell me why on Monday. Have a great weekend.